Let's do Lewis. I'm going to do a couple quick ones just to feel like I'm doing something. Okay, here, I've been like making progress on this list. I like to check things off. Lewis acids and Lewis bases. Anything can be a Lewis acid and base. I'll kind of define it like this. The Arrhenius has the smallest definition base of which it can apply to it. Bronsted-Lowry, which defines in terms of protons, is a slightly bigger space or number of molecules that occupy it. And then Lewis acids and Lewis bases occupy the largest. So Lewis acids and bases, that definition includes the other two. So what I would do, what you've seen me do, is I always start here. Bronsted-Lowry and base, based on the proton. And then, oh, I see a hydroxide, so I'll go to the Arrhenius definition, because Arrhenius focuses on the hydroxide for the base. And if none of those two work, then I'll go to Lewis acid and base, because it typically involves the most thought. So that's my logic flow when I look at something. Let's say we have, I think this example will work. Yeah, let's put up I here. Okay, let's look at this reaction. I want to know what's the acid, what's the base. Well, you see no protons moving. So there are hydrogens, but they're not moving. So then I think about hydroxides. No hydroxides, so I can't go there. So now I'm thinking, okay, I better go to Lewis acids and bases. And not always, but you'll see often, we'll say, hey, what's the Lewis acid in this reaction? Or something of that nature. Okay, so you want to see what happened. This bond, which was here, is broken, and we formed this bond. So what that means is the Br must have attached here, and this iodine broke off. If you draw on the lone pairs, which is often helpful when you're doing this type of problem, you'll see, and this would come from the Lewis structure, you would see that, this, this, and this. Okay, so this one was an electron pair donor. So donated, this one accepted the lone pair. So an electron pair donor is called a Lewis, yeah, this is the Lewis base. An electron pair acceptor is called a Lewis acid. Okay? So there's typically, we don't talk about conjugates in this case. So when we ask about Lewis acid or base, we're talking about the reactants. Another way you could have identified it is a Lewis base is typically going to be it's an electron pair donor. So you're looking for something that has negative charge. Not always, but it's common, or extra lone pairs that it's going to do something with if it's neutral. That can be fairly common. Okay? Alright, so that's a classic Lewis acid, Lewis base, and that's how I get to, after I exhaust the other definitions, I go to that definition last. Yeah?
Are the lone pairs on the central atom, or can they be on like that?
Where are you going to find the lone pairs? There could be a generalization, but I'm not sure. Hard to say. There's so many options with Lewis that I'd hate to generalize and then you see an example that's contrary to that. Okay, next. Let's do the how to solve. That's a big question. And I think we'll get to X is negligible. Okay, I want to highlight something that's in the reader. I'll show it to you as soon as I flip over there and find it. Flipping pages currently. Okay, here we go. Let's start here. This is page 113 in the reader, bottom. Types of problems that involve the ICE table. Let's start here. One thing that's super helpful is for you to know when to use the ICE table. Okay? The ICE table is when you're looking for an equilibrium concentration. When you're finding pH, you need an equilibrium concentration to do that. So some pH problems involve an ICE table, not all. Okay, chapter 14. This is from the reader. So this is a chemical equilibrium chapter, if you don't have my reader. That anytime we ask for an equilibrium concentration or a partial pressure or a total pressure if we're including Kp. Sometimes it might say equilibrium pressure, but I think it would usually say partial pressure. For chapter 15, there's a couple areas. So when you're finding the pH or sometimes equilibrium concentrations for weak acid, weak base, salts or ions that are acid or base, and then weak polyproducts. Those are the scenarios you would use it there. And then we haven't done all the chapter 16 ones, but a common ion or a buffer. However, for common ions or buffers, as long as they're a buffer, you can use the Henderson-Hasselbalch instead of the ice table. So here's part of the discernment. If I see a common ion or a buffer, common ion meaning it is a buffer, I'm going to use the Henderson-Hasselbalch because that is the ice table in shorthand form. Okay? If it's one of the others, then I have to literally use the ice table, the ones above it. Okay? So that's when it's this kind of problem, that's how I'm approaching math style problems. Buffers, you're clearly seeing two things in it and they're conjugates, and it's asking about a pH. Unless it sometimes literally uses the word buffer. For all the rest, there's going to be one lone chemical of interest there, and that's how you'll know, okay, this might be an ice table if it fits in the weak category, and I'm asked for, say, a pH. Kind of a slight variant on this, and also not a common problem, but people got excited about it when I did it in class, is a dilute strong acid. A dilute strong acid, the way I solved it in class, it sort of looks like an ice table, but I just made up a technique to solve dilute weak acids or weak bases that looks like an ice table, but technically the proper way to solve it doesn't really use an ice table. Okay, that was just my method of solving it when you saw that in class. Okay, now I want to turn the page. I believe, oh, is it here? I hope, okay, nope, it's not, I didn't put it in this chapter. Let me flip back down to chapter 15. I want to show you one other thing. I'm looking on the bottom of page 91. Now, case summary. There's a lot of K's that you've learned in this class. Except for Kp, they're all concentration Ks, or Kcs. So it's like Kc was prolific and had a lot of babies, and these are all the babies that it had. It's going to have more before the class is over. Okay, so you should know all these kind of conceptual things that I just summarized here. So when, hello, is a K value small? Ka or Kb if they're weak, or Ka1 for a weak polyprotic acid, and then Ka2 and Ka3 are always small. They're successively smaller on several orders of magnitude. So Ka3 is much smaller than Ka2, and so on up to Ka1. What K values are large? Ka and Kb for strong acids, or Ka1 for a strong acid. We don't know if it's just a generic Kp or Kc. It has no attachment to large or small numerically. Okay, then finally, this is related to X is negligible. These are the scenarios where X will be small. So, whenever you're doing a weak acid, weak base, or Ka1 for a weak polyprotic acid. So those are all the scenarios where you're going to assume X is small. There's two assumptions that you'll make. Let me go over because this fits into one other category. If you want to double check that X is small, so you're double checking your assumption, and these two will hold later in the course as well. You can take, one way is to take the molarity over K and ask if it's greater than 100. If that's true, your X is going to be negligible. Two, which is true for weak acids, weak bases, weak polyprotics, or buffers. It's going to work. The other way is the percent ionization, which is X over the molarity times 100, and then I don't know what other classes did, but I called this the 5% rule. People in other classes, did you learn the 5% rule or something different? Or a 10% rule? Or no idea? Okay, you have to know this because it's the percent ionization, which is a key concept. Or it's the percent, really the percent a reaction goes forward more generically. So it's a percent forward. It's a F forward. Okay, so I'm always in class going to use the first one unless I'm asked for the percent ionization or the percent going forward. Okay, let's see, X is small. So there's the percent ionization. I want to say one thing about the percent ionization before we get off of that topic actually. There's two ways to ask you a percent ionization problem. Here's way number one. Well, let's write a generic acid, HA. I'm going to do like a classic pH, ice table, that sort of stuff. So I go, okay, let's write the general reaction for an acid. By the way, make sure you can write this action out by the time you get to the exam with state symbols. Okay, we will ignore water, it's a liquid. Typically these are 0 for a weak acid, and I've given some molarity M right there. So then I'll say, okay, minus X plus X plus X, and minus X, X, X. And then K, A is X squared over M minus X. We're going to assume X is small. K is given where? Back of the exam. That should be true for the other instructors, but you can ask just in case. I'm going to solve for X. Let's go to the next slide. This is your classic weak acid problem. You're going to solve for X, and then pH is going to be the negative log of X. Okay? Alright, so you got that going on. Then we ask you the percent ionization. And you'd go, okay, that's 100 times X, which you just found, divided by the molarity, which you're given. Okay, that's a classic way to talk about percent ionization. The other way to do it is if I give you the percent ionization and I ask you for something else, for example, the molarity or Ka. So the other way is give the percent ionization, ask for, it can be worded a couple different ways, but ask for Ka, no comma, or the initial molarity or something like that. So in that case, you're doing the same problem, the same thing but backwards. Mathematically, it's usually easier to go backwards. But some people get tripped up when you're making your way backwards on these kind of problems. Okay, those are the classic percent ionization type problems, if they're math related. Okay, next. Acid-base neutral. Boom. Okay, here's how I do an acid-base or neutral problem. Remember, it could be one, identifying if something is acidic, basic, or neutral qualitatively, or a quantitative. You got to figure out if it's acidic, basic, or neutral, and then solve an ice table for a pH, which would be different if it's acidic or basic or whatever. So, let's say you had KNO2. So I want to know, is this acidic, basic, or neutral? The way I do this, if you have another way, that's totally fine, but my style, and you can do this in your head once you get used to it, is to write the ions separately, because you got to think, okay, what are the ions? For me, it's helpful to think about the ions by thinking about the conjugate of each ion. So here's the conjugate of each ion. So that's the lowest levels conjugates. I think about what the heck is the conjugate, and that helps me figure out what the ion is. This is what? Strong base. The conjugate of a strong base is neutral. Okay, so I'm partway there. This is a normal weak acid. So this is a normal weak base. A neutral plus a base, this is basic. So that means I would, if I wanted its pH, I would need a Kb. Where would I find the Kb if I wanted it? Kind of. You could go back here, but the problem is what? Yeah, you're not going to find a Kb for NO2 minus. You need to find its conjugate, HNO2, right here, nitrous acid. There's NO2 minus. This is a Ka, 7.2 times 10 to the minus 4. So you go, okay, Kb would be Kw over the Ka of the conjugate, 1.0 times 10 to the minus 14 over, what was it, 7.2 times 10 to the minus 4, I think. So you would do something like that to get the Kb. No, not something. You would do exactly that. Okay. And so then you could do, say you're given a molarity, then you could use an ice table to find the pH. Okay. There was a variant on this that people got really excited about and somebody asked me about, so let's do this now. Is it okay, did you ask me that it's baking soda? Is it okay if I pick something else? Okay. So I did a baking soda problem in class, but let's do like a variant on that. Just so people can see something different. I wanted to know if this was acidic, basic, or neutral, which is a bigger problem. That there's an easier version sometimes of this that you would see on a multiple choice concept, typically. Here you write out the ions separately, and you would say, oh, hey, that's KOH. That means this is a strong base, and this is neutral. Cool. The problem with the anion, though, HSO3 minus, is this could be acidic or basic because it's within the realm of polyprotics. Meaning, if it was basic, then its conjugate would be H2SO3. If it was acidic, its conjugate would be SO3 2 minus. So the top one is it grabbing a proton, the bottom one is donating a proton. That's because, so let's do a little scratch work at the moment. Oh, this is also going to do polyprotics. This is awesome. Okay, so H2SO3, I'm doing like several of your questions here at once right now. Okay, so you should be able to write these kinds of reactions for polyprotics. Here's the first loss of the proton. Make sure you put state symbols in as well. Okay, there we go. All right, the first one, its K is called Ka1. The second one's Ka2. So you would need to know that I just wrote in black right there, and be able to generate it like I did. You wouldn't have to memorize the numerical values of K. We'd have to give that to you. Okay, if you go back to the problem in blue now that's at the top, after I wrote what's on my scratch paper there, I would say, okay, if this is acting as, let's say, an acid, then HSO3 minus as an acid would go like this. It would donate a proton as such. And then I would have to ask myself, oh my gosh, which K is that? You would look at your reference sheet right here written in black. Oh, that looks like Ka2. Done. Okay? So that's Ka2. Again, I'm trying to figure out if this is acidic, basic, or neutral. I don't know, because that could be an acid or base. Let's write that in the ground. This could be an acid or a base. So I'm having trouble figuring out if it's acidic, basic, or neutral. So I look at it acting as an acid first. A for acid. Okay? Then I'm like, cool, that's good. Now let's look at it talking about as if it acted as a base. As a base, now it's going to receive a proton, and water is going to donate that proton, become OH minus. Here's the problem with it acting as a base. That's neither one of these here written in black. Okay, so, but it kind of looks like the first one, almost. Okay, so here starts a more typical multiple choice style question. The multiple choice style question would be, given this random looking reaction, what's its K value? That would be a pretty typical question. And this is related to Hess law, but for K values, not for delta H's. Okay. So in that style of question, you would have had to realize, so this is my important reaction right here that I'm trying to figure out. I would have to say, okay, that reaction kind of looks like that one up there in black. So I'm just rewriting the one up there in black. And that's a Ka1. And it kind of looks like the Kw reaction, the ion product of water. You might be asking, how the heck did you know that? It just always happens that Kw is involved in these kind of questions. So, the first time you see it, you'd be like, oh, it feels more random for sure. So, now if I look at these two reactions in black and think, how can I add these to get to the blue one? I'd say, well, SO3 is here and here, and this is, H2SO3 is here and here. What if I just flip this reaction? It'll look a lot more like the top one. So I'll flip it by multiplying by -1, and the Ka value does what? It inverts, so it raises to the -1. And then if I literally add it to this one, because the OH minus matches and the water matches nicely, let's just leave this one the same. Multiply by 1, or raise this to the 1. Then you can add those and you get the blue one, and that leads you to what you want, which is the K for this reaction up here in blue, this one, where my pen is right now, is just, when I add these reactions, what happens to the K's when I add two reactions? They multiply, so it'd be Kw times Ka1 to the -1. So now, I don't have the numbers because I just made this up, but you would have to compare this numerical value of K and that numerical value of K, whichever one, sorry, I circled the wrong one, don't circle that one. This value of K and that one, whichever one is larger would tell you is it an acid or a base. So if the top one is larger, it would be an acid. If the bottom one is larger, it would be a base. Okay, again, a more classic style question would be just what's down here at the very bottom. Yes?
I'm sorry, can you do the last thing you just said about
If you look at these two values here, the larger one will tell you if this is an acid or base. If the K for this acting as an acid is larger, it's an acid. If the K for this one acting as a base is larger, that's a base. Okay, polyprotics. Let me say a little bit more about polyprotics since we're kind of on it. Couple things that you want to know about a polyprotic. Given any polyprotic acid, you should be able to write all the reactions out, K1, K2, etc., whatever exists. You should be able to write all the K values, and then the classic style question is, what's the pH? And what are the equilibrium concentrations for all species? So, for that kind of problem, I said this earlier, you would only need an ice table if the polyprotic acid is weak. If it is strong, you don't need an ice table to solve that problem. The K1 value is much larger than K2, which is much larger than K3. The other thing that is helpful to know, yes, if you look at what's here, if you look what's here in black, right here in the middle of the screen, there we go. Let me number these. 1, 2, 3, 4. I numbered that one, this is 3. I already numbered that one, that's 2. 5, and I already numbered that one, this is still 4. So I numbered each molecule 1 through 5. Which one, 1 through 5, at equilibrium will have a molarity equal to Ka2? Glad I asked. Definitely 5. So it's the one that has lost 2 protons. That entity will be equal to Ka2. Okay. All right.
This question, when you're solving for the base reaction, and you
Go ahead.
when you're solving for the base and then you flip it, what if the H2O's cancel out, but then there's the 2 H2O on one side?
Yeah, so one of the H2Os will drop out and the other one will stay, which you need that in the overall reaction. One should drop when you add the two reactions. There's 2 on the bottom reaction, and then 1 right above it. 1 will cancel out, and then the reaction I wrote in black, I believe, has 1 H2O there. Yeah, that's what you want. Yep, which will cancel with that one to leave a net of 1. Good? Okay, cool. Okay, next. Let's see what else we got. And let's see what time it is. Oh my gosh. Okay. Oh God, oh yes. Okay, I think we'll finish with this. Whoa, whoa. Okay. Let me see how much I can do. I do have an example problem. Yeah, let's try this. This is more for acids, this first one. I have to take a picture of it. The words are kind of irrelevant. Okay. In this problem, we want to determine acid strength. Notice in these examples, as it says in words there, part of these amino acids are always the same. So I'm going to put a little line where the half of it is always the same. It's this section right here, and this one right there. See how that side of it always looks the same? Let's jump down to this one. This right there. This right there. Do you see how half of it is always the same? And then this one's probably the trickiest visually to see. It's right here on that one. So hopefully you see I'll box the section. So that's all the same for that section. All the same. That's the same. Same. So what we're doing on this, the part that is not circled is called the side chain. We're looking at we want to rank those in terms of acid strength for the side chain. Okay? So let's do at least the easy ones. There's 1 or 2 that are a little crazier. Okay, and I want to number, let's put letters here. So we'll go A, B, C, D, E, and F. Just to give them letters so we can kind of refer to them easily. Let's see, what's 2 that are good to look at? Let's look at A, D, and E. Let's look at those. Do we want to look at? We'll look at C and F in a little bit. Let's look at A, D, and E. Okay, so what you want to do when you're looking at these, are those good ones to look at? I want to look at ones that are not too painful first. No, let's do an easier one. Let's do, yes, here we go. F and B. Let's start with those 2. Let's start with F and B. Okay, you look at F and B and you try to figure out what's different. For F and B, you see that B has an OH group and F has an SH group. So when you're looking at those 2, B or F, which one would be a stronger acid? F would need to be a stronger acid than B because you're comparing 2 things with different elements. One has an O and the other has an S. So you're looking at a periodic table. This is the concept of polarizability or size. As you go down the periodic table, you're becoming a stronger acid. So between B and F, I would say B is a weaker acid than F. Okay. All right, let's compare another 2. Which one would be, I'm trying to think of which would be another good. Let's go, oh yeah, let's go, where's that one? Let's do A versus, I should put a versus here, that sounds more antagonistic. A versus, where is it? B, there we go. A versus B. Which one of those two would be a stronger acid? Yeah, you're comparing, A has a longer chain, that's true, but you're kind of really comparing the nitrogen with the oxygen. Okay? So you're looking along the row of the periodic table. You're comparing nitrogen and oxygen. You need to remember, because of electronegativity, as you go to the right on the periodic table, you're becoming a stronger acid. So, B would be a stronger acid than A. Okay, let's see, I think, oh yeah. And so now let's compare A versus C. A and C, which one is a stronger acid? Oh, this is going off screen. Yeah, A and C again, you're going along the row of the periodic table. On the top there of alanine, you've got the CH3 group, which is not drawn in, and then an NH2, so a C versus an N. Look at the periodic table, carbon versus nitrogen. N is more to the right on the periodic table. So, which one was it? A will be a stronger acid than C. So you basically want to use, and I put this as a summary here in the reader, you want to look through the sort of things I'm looking for. I'll put this back in just a moment. The sort of things I'm looking for as a quick snap judgment are look for atoms that are more to the right and down on the periodic table. That's the one we focused on. Those will be stronger acids. I'm going to look for electronegative elements. I'm going to look for withdrawing groups or more oxygens and double bonds. So I'm basically focusing right here to make my initial decision. If it's harder than that, then I might have to draw out a Lewis structure. If it's a base, let me say one more thing and then I'll take your question. If it's a base, it's exactly the opposite. So if you're looking for a base or a basic center, you want to look for atoms that are more up and to the left on the periodic table, for example. Or no resonance, things like that. So it'd be exactly the opposite of what you're looking for here. If you're looking for a basic center, as opposed to comparing bases, all we're doing is, so need to keep this off for just a little bit as I do another example here. If you're looking for a basic center or an acidic proton, either way, let's do the proton for a second. It would be as if you're doing, let's say with CH3, CH2, SH, and CH3, CH2OH. If you're comparing those two, you'd say, okay, because sulfur is lower on the periodic table, this would be a stronger acid. But if you're looking for the most acidic proton, it's that sort of problem, but as if these two are connected. So if you went, if I have SH, CH2, 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 OH. Where's my most acidic proton? It's still this one. It's just those two molecules are connected now. So when you're asking what's the most acidic proton, you're basically looking for protons on the same molecule as opposed to molecule versus molecule versus molecule. If you're looking for the most basic center, it's the same idea. You're looking at one big molecule with a bunch of bases all connected versus the bases listed separately. Yeah, and there's two questions. Okay, good. Just to clarify, the acidic proton is literally always the proton. So it's going to be this one versus this one here, or that proton versus that proton there. But the one that is most acidic is the one on the sulfur in both cases. So the sulfur is not acidic, but the hydrogen on the sulfur is the acidic proton, or the most acidic proton. The sulfur is what makes it acidic, because the sulfur on the conjugate base is more stabilized. Yes, you have another question.
So let's say someone has these two molecules and then maybe just each has a carbon, a long carbon chain, but there's like nothing else, like no other element shorter tail you want to sit in?
You want this
Or like,
versus this?
or like, what if like there was none at all? Like, would it be considered safe at all?
No carbons?
Or like, because in the previous example, there was one that had a long tail and then the nitrogen at the end.
Yes.
What if it didn't have a nitrogen? It didn't have a small,
Then it would just be considered a carbon. CB. Yeah, if it was, if you just had this, for example, attached to something, you're just considering CH3 here. So just think of carbon itself. This or this? I probably wouldn't give this to you. This would be a little tough because it goes through the sigma bonds, and these are kind of far away, but they are electron donating. So you would tend to think the thing with more, that can donate more carbons, would be less acidic. Yeah, tends to be. But this is a little weirder because it's in a long chain as opposed to something like that. Yeah, yeah. So with a long chain, that'd be a little tougher to give you all. Yeah. Okay. Let's see if there's, what else I have. Oh, I'll put this back up if you didn't get it. If you want all the answers, I don't think I'll do it right now, but if you want to rank them all, the strongest acid is, it goes in this order. D to, I labeled F.
We can't see it.
But I can. There. Okay. Then to tyrosine, what is that? E to 4B to A to, oh, whoa. Let's see. Okay, that's the order if you want to look at it all. Okay, let me see our list, see where we're at. I do want to say one thing about KP before I go to general questions. Sorry, I didn't have time to get to colligative. You can ask me during the specific question part. KP, there's a couple styles of questions that I wanted to highlight. One is, it could be just finding the equilibrium partial pressures, okay? Another style that's really similar to that can be added on top of the equilibrium partial pressure is to find the total pressure. If we're asked for the total pressure, you need to find all the equilibrium partial pressures from the ice table and then add all your answers. So you can find the total pressure. That would be a pretty common style question. Another style is converting from KP to KC. So what I would do if you're having an equilibrium problem and we give you, say, pressures for the units of the molecules in a KC, I would just convert the K so it matches the units of the molecules. I think that's the easiest way to do it, but you can go either way. And then another style question is in the multiple choice, where we might say something like, in which of these cases is Kp equal to Kc? That's a pretty common style question. In which case you're looking for where the change in moles of what state? The gas only, because of the ideal gas law, where the change in moles of the gas is equal to 0. Okay.